We're going to look at the reactions that acids participate in. The first reaction is the most common. It is a neutralization reaction. It is a double replacement that occurs between an acid and a base. It occurs via metathesis, which means there's going to be a phase change in one of the products. With a neutralization reaction, we have an acid and a base. It's going to form salt and water. An example reaction is if we have hydrochloric acid reacts with sodium hydroxide. Acids, or compounds that have hydrogen, tend to take on their ionic properties as that cation. Remember, with metathesis reactions, your two products need to be of the same compounds as your two reactants. HCl being an acid, it is a molecular compound even though it can form ions, so we need to make sure we have a molecular compound on the other side. Sodium hydroxide is an ionic compound, therefore we need an ionic compound on the other side as well. So with HCl, these have to be in their aqueous forms in order for the reaction to take place. Hydrogen can act as a cation when it's in its aqueous form. Chlorine will be the anion. Sodium is going to be a cation, and hydroxide is going to be the anion. As with metathesis reactions, you're going to have an ion switch place to reform. So HCl is our molecular compound, sodium hydroxide is our ionic compound. On the other side, the way in which these swap, sodium's now going to be with chlorine, and that's going to stay aqueous as it makes sodium chloride, which is a salt. And then hydrogen, is going to go with hydroxide, also known as H2O, or water. There is that phase change. We formed a liquid from an aqueous solution. Therefore, we have a net ionic equation. That net ionic equation is looking at the hydrogen ion and the hydroxide ion. That forms our liquid water. And that is what a neutralization reaction is. We can have single replacement reactions that occur via oxidation reduction processes with our acids. What is required is we're going to need a reactive metal and that acids, particularly strong acids. Weak acids are not very good. We have this chart that looks at reactivity of metals. At the bottom, platinum is the least reactive metal, all the way up to potassium. What needs to happen for this to occur is the metals need to be more reactive than hydrogen in order to force it out of solution as an ion. So anything above wants to be an ion preferentially over hydrogen. Below, they want to stay neutral. All right, so if we have zinc and we put it, and this is a solid, and we put it into a solution of hydrochloric acid. And that hydrochloric acid is aqueous because it needs to be that ion form. Zinc is above hydrogen, so zinc is more reactive than hydrogen, which means it preferentially wants to be an ion in solution, forcing hydrogen out. So zinc is going to force our cation hydrogen out of solution, causing elemental hydrogen to form, and it's a gas in its elemental state. Remember, hydrogen is a diatomic element, Brinkelhoff. It's part of the Brinkelhoff series. So when it comes out of solution, there's going to be two of them. And then zinc's going to go into its solution as zinc chloride, and so that it can be aqueous, and zinc becomes that ion. Of course, we need to make sure we have a balanced reaction. If we did this with copper, this reaction would not take place. So copper cannot neutralize an acid. The only way we can neutralize an acid with a metal is to make sure the metal is more reactive than hydrogen, which means it wants to be an ion more than hydrogen does. The last reaction with acids is a metathesis reaction. But in order for this metathesis reaction to occur, first the reaction undergoes double replacement. But one of the products in that double replacement undergoes dissociation. Dissociation is when we put a compound in water and it forms its ions in aqueous solution. However, with some dissociations, we get a state of matter change. With these reactions, we call the bases that we react with are carbonate or bicarbonate ions that are in a salt form with a metal. The most common reaction that does occur with this is we'll have hydrochloric acid reacting with calcium carbonate. This is a reaction that can happen in the ocean. Calcium carbonate is what makes up limestone or the shells of clams, oysters, lobsters, stuff like that. And so when acid reacts with the calcium carbonate, it actually causes the calcium carbonate to break down. This being a double replacement, the cation of hydrogen is going to replace the cation of calcium. These are aqueous. So we're going to form calcium chloride, which stays aqueous because it is an ionic compound, and we've got to make sure that we follow our types of compounds forward. And then our molecular compound is actually the formation of another acid, carbonic acid. Now carbonic acid, or all acids, dissociate in water. So what happens is the metathesis reaction is not complete because we have not had a phase change. But because one of the products is an acid, it undergoes dissociation. With this dissociation, it's going to split and react and break apart. When this happens, it's going to form CO2 gas and water. There is our phase change. So in order for this metathesis process to work, it undergoes two reactions. Like we have done before, we can then combine the two reactions, cancel what's common on both sides of the arrow for the complete reaction. Therefore, HCl reacts with calcium carbonate to form, because our bicarbonate or our carbonic acid gets canceled out, we get calcium chloride, CO2 gas, and water. You may have seen these reactions if you've used Tums. Any acid reflux, alkaloids, they are made of these carbonate ions. If you've ever put baking soda into vinegar, same process occurs. So that bubbling is that CO2 being formed, and that CO2 is going to bubble out, and you're left with salt water, just like a neutralization reaction. Just the process of the neutralization occurred with a carbonate ion versus a hydroxide ion. But in the end, we get that metathesis, we get salt, we get water, and that gas escaped from that carbonate ion.